I guess I talked a lot about these text-based games, right? So let's take a little bit of a shift from that kind of an environment, right? And talk about some other environments which might be interesting to explain this idea of dynamics, right? So when I say dynamics, right? So this is basically referring to an understanding of the world, right? So as humans, if I tell you I'm pushing the bottle off the edge of the table, right? Immediately in your mind, you're probably imagining the bottle is falling down from the table, right? So you have an understanding of the physics and how things work in the real world, right? Or if I say like I throw my phone into the river, you can immediately imagine it's too heavy, it's going to drop down into the river, you know, and then the water is going to damage the phone, and you know, it's probably lost forever, things like that. So you have a very good understanding of the dynamics of how the world works, like physics and things like that. But our agents really don't have that, right? And in reinforcement learning, the idea is like you learn everything just by interacting with the world, right? So in this piece of work, this was back in 2018, what we wanted to do was, you know, instead of just getting agents to, you know, try different actions and learn just from rewards, we wanted to say, okay, agents should also be able to learn from manuals or guides, right? Like similar to how a human would learn, right? So here's an example of a couple of environments, right? Like think of them as just like games, you know, these are basically, you know, similar to your games that you play on the console or something like that. So this is an agent that's moving around, you know, maybe you've played this game, you have to collect all of these diamonds. There are some scorpions that'll try to like chase you and, you know, kill you on touch and so on, right? So, and then this is another game where I guess this Bomberman where, you know, you place some bombs, you blow up the tiles and you can move around and so on. So the idea here is that, you know, we assume that there's an agent that learns to play these different games. But what is different from a traditional reinforcement learning setting is that we also provide the agent with some descriptions of those environments, right? So assume I give the agent, in addition to rewards in the game, I tell the agent scorpions chase you and kill you on touch, right? And in this game, I say spiders are chasers and can be destroyed by an explosion or something like that, right? So the idea here is like these descriptions sort of provide useful information on the transitions and rewards, right? And they can be partial, they can be noisy, but they help you learn the game faster, right? So think of yourself playing this game. So if I didn't give you this description at all, then you just have to like, you know, play the game for a few times, figure out what is worth getting, what's not worth getting. But if I give you this description, you already have an advantage, right? So immediately you will start off probably playing the game pretty well, right? So what we basically want to do is like try to use language to augment learning from rewards, not replace it. We just want to make the agent learn from both the language, the text description, as well as, you know, the rewards in the game itself, right? Just play the game, figure out how things work. So this is what we did, you know. So our setup was basically, you know, you have a source game, right? So you learn a policy on a particular game, right? Where you also have descriptions. And during this whole training process, what we do is like we learn a transition function and a reward function that is conditioned on the text. So what this transition function is basically telling you is, given a state S, right, like a frame that you see, if you take an action A, what is the probability that you will see the next state S prime? Okay. Think of this as similar to the physics model that you have in your head, right? Like, so if I push the bottle off the table, what's the probability it's going to just stay, you know, in midair versus just fall down, right? So that's the kind of function that we want to learn, but conditioned on the text, right? So if I now tell you you're on moon or on Mars or something like that, where the gravity is like much lower on the moon, let's say, then you will assume that the bottle will fall much slower than let's say if you're on the Earth or something like that. So this is similar with the reward function. So what we do here is basically we learn all of this on one game, okay? And then when we transfer to a new game, so the agent now tries to learn a completely new game, right? Completely new, no relation to the previous game. It's now provided with these descriptions Z2 that's talking about the new game. So now, even before interacting with this new game, right? Even before playing this game a few times, the agent already has an idea of how things work in the new game, right? Like it knows that the spider is going to chase you, so it can have an estimate of the new transition function as well as the new reward function even before interacting with the game. So basically our idea is like we can use this to bootstrap learning and make learning much, much faster than just using reinforcement learning all over again. So the idea here is to make reinforcement learning more generalizable, such that you train on one particular environment, you should be able to just transfer to new environments, right? So this has applications in many different scenarios. So if you, for instance, like even within games, if you want to play Go and then you just want to take some strategies to chess, you could do that. In robotics and things like that, if you learn, if you have a robot to perform a particular task, like pick and place or something like that, and then you want to use it to push objects around, the dynamics works the same, right? Like the object moves around with the same friction, different friction, and so on. So you should be able to provide that information and just adapt policies to the new environments. So here are basically some experiments that we did, right? So we had a bunch of different game environments from this framework called GBDAI. We got people to describe these games. So we used Amazon Mechanical Turk and just asked people to, play these games, describe things like this, like scorpions and spiders and so on. And then we basically trained our model on multiple source tasks, multiple of these games, use these parameters to initialize for the target tasks. And then we had baselines, these are like some standard reinforcement learning algorithms, some previous transfer algorithms that were proposed and so on. So on the right-hand side, you can sort of see the difference, right? So if you don't do any transfer, right? You just learn a game from scratch. This is the average reward you get over a few epochs, right? So remember that the average is basically giving us an idea of like how well the policy is, as well as how fast the policy is learning, right? So you take the learning curve and simply take an average over a particular time period. So no transfer is around 22.22 reward, and the DQN and actor mimic, which are some baselines, don't do very well. Text DQN is simply using a DQN reinforcement learning agent and just adding text as input to it. It does slightly better because it has some extra inputs. But you can see our model, which is the thing that we call text win based on the value attrition network. It has a much, much higher reward because it's able to understand the dynamics and rewards more explicitly and learn how to play these kind of games. So there's been other work along these lines, right? So in 2011, Branovan, David Silver, and Regina Barzilay had this paper about playing Civilization, which is a very, very popular game, by using text manuals, right? So the manuals will tell the agent what to do, and they were able to beat, the built-in game AI, more than half of the time. More recently, there was a paper by Zhang et al., which also is doing something similar in terms of like how you would want to reason about information provided in the text and use that to operate in a particular environment. So this is some very new work that we have, which is led by my student Austin Wang. So the idea here is that all the works that I showed you in this section, right? They all assume that some form of mapping has been provided between entity symbols in the observation and text. So when I say mapping, right, what I mean is if you have sort of descriptions like these and you have games like these, the mapping that's provided is the fact that this bear, the word bear, actually means this object, okay? So this sort of mapping is actually provided to the agents that I talked about. Now, in this work, what we wanted to explore was, can we learn such a grounding without any prior knowledge? Okay, so to sort of put it into a different context, right? Like this is how children learn in some sense. So as a baby, a kid doesn't really have an idea of like what a glass is, right? So, and then the kid will play around with the glass, and multiple times the parent will say, okay, don't touch the glass, or touch the glass, give me the glass. So it's repetitive sort of nature where, you know, the kid hears the word glass multiple times whenever it goes near the glass, sort of gives it a grounding of what the word glass actually means, right? To be able to map that to the object, the glass. So that's what we basically want to do with this setup. So the idea is, you know, we're going to have multiple different environments like these, and just a bunch of descriptions that go with the environment, but we don't tell the agent what is what. We don't tell the agent that this is the wolf, this is the octopus, this is a knight, nothing like that, right? So the agent has to completely figure out what word is talking about what entity just by, you know, interacting in the environment itself. It just has to move around, figure out what rewards it gets, and so on. So for this, we basically, you know, used an approach of multitask reinforcement learning. So we basically set up an environment where there are like 44 different games for training, 32 games for validation, 32 games for testing. And note that this is not really common in reinforcement learning because, you know, most of the time we train and test on the same game, but this is sort of like a different setup because we want to make sure that we want to generalize to new games, right? So we don't want to train and test on the same game. And then we, again, collected some, you know, all of these descriptions were collected from Amazon Mechanical Turk, basically free-form text, right? So we've asked people to just watch what happens in the game and sort of provide these kind of descriptions. Okay, so the model, again, like maybe I won't go into too much detail because it's basically a big neural net that, you know, has some attention mechanisms to basically attend to a particular entity and a particular sentence that's talking about that entity at the same time in order to, you know, produce actions that make sense. Okay. So here are some results, right? So as you can see, you know, there are a couple of baselines that don't really make use of the text. So for instance, you can just sort of train a multitask model that just conditions on the game ID, you know, that doesn't do very well on unseen games because it has never seen those games before. We also checked a mean bag of sentence kind of representation. So instead of having this whole complicated attention mechanism, we can just take a mean bag of words kind of approach over all of these descriptions, simply encode them and feed them into the model. But that doesn't do well as well because it doesn't really do the fine-grained mapping between observations and the sentences themselves. And finally, you could see our model, in fact, is able to transfer quite well to unseen games. So again, these games are completely new games. The model has not seen them, and it's able to win like 86% of them, which is quite big. And you can see here's sort of like the grounding it learns. And surprisingly, you know, it actually learns the right grounding. So these are the objects that are on the row side, and these are the descriptions of those objects. And it's actually able to attend to the right object most of the time, right? So you can see how like the attention map is maximized in along the diagonal, which means that it knows that, you know, a dragon is actually the word dragon, egg is related to the word egg, and so on. I mean, there are some cases where it's a bit confused, like the wolf case, right? Like you see this row, you know, it has confusion between, I mean, it still thinks the wolf is related to the word wolf, but it also has high values for dragon and knight and so on, just based on their dynamics and how they act. Okay, so that was basically talking about, you know, how we can ground language, right? So into you know, the world around us, right? Like how can you like understand the semantics of language and map it to the world so that you can actually use it to understand what's going around you and how to build agents that do the same, right? So another way of thinking about dynamics is thinking about how to learn with constraints, right? So this actually probably has a lot of connection to robotics specifically. So the idea here is reinforcement learning is great, but, you know, if you just apply reinforcement learning to robotics, it's not great because reinforcement learning naturally involves some exploration, right? So if during that exploration, let's say the robot just like, you know, hits the wall very hard, the arm is going to break, right? And you don't really want that. So we want some way of, you know, providing some constraints on the learning, right? And so for instance, like maybe you don't want a robot to step out of a boundary. Maybe, you have a Roomba, you don't want it to, fall off the stairs or something, right? Or you don't want it to go on the carpet, right? So you want to provide some boundaries. You have like a drone that's in this case here, and you don't want it to fly into windy areas. So this is a fan that's blowing. The drone flies into the wind, it's just going to crash, right? So the idea here is to allow for reinforcement learning. The agent has to explore the environment, figure out how things work. But at the same time, you want it to be constrained. You don't want it to explore too much in certain unsafe states and, potentially break itself or harm other agents around it. So this is, in general, yeah, this is the area that's called safe reinforcement learning, and it's really coming up now. And the way that people normally approach this is by, specifying some cost functions, right? So here's an example where, you can try to maximize the reward, but such that your distance of the policy from some target policy is bounded by some delta, right? So you say like, okay, I don't want a policy if I'm like a humanoid robot or something, I don't want a policy that just jumps more than 5 inches off the floor, right? At any point of time, things like that you can specify. So this is great, but you can imagine, right? Like specifying these kind of things in math is not very easy or very fun to do because you need experts. You need experts to be able to specify these kind of constraints, logical forms, math, and so on. So what we wanted to do was instead say, hey, like, why can't we just do this in natural language, right? This is very, very natural to humans, right? So if you wanted to tell a robot to not do a certain thing, imagine you can just tell it in plain English or Korean, right? So basically, language is a very natural medium of communicating these constraints, and can allow for better human-robot interaction applications in robotics, self-driving cars, dialogue systems, whatever sort of systems that we want to make sure that the learning is controlled, right? So importantly, this is not the same as instruction following, because we're only telling the agent what not to do. We're not telling the agent what to do, right? So you can have, a vacuum cleaning agent or like a Roomba, or you can have, a humanoid walking around. You can have, I don't know, several kinds of bots, but you can instruct all of them that with the same thing, right? Whatever the task is, you can say something like, do not enter that room, or do not walk on the carpet, things like that. So here's an example, right? So this is an environment that we built. I can sort of I'll give you more details, but this was led by, yeah, of course. This is an archive led by my students, Jimmy Yang and Michael Hu. And the environment here will give you a sense of that. So imagine you're in this environment, you're the agent, right? So let's say you're this red triangle, you're the agent, and you're moving around, and you have to collect these sort of different things for rewards, right? Like this key, this red ball, this ladder. If you go on these, you get a reward. But then, I provide you constraints like this, right? So I can provide you constraints saying the lava is really hot, so it'll hurt you a lot. Don't walk on it more than 3 times, right? So then, you'll have to find your way such that this lava square, the orange square, right? You don't walk on this more than 3 times, right? So as you're exploring. So that's an example of what we want to do, right? So the model that we have itself is basically based on 2 different things, right? So we need to do 2 things. One is we want some natural language processing model to convert a constraint that is specified in English, let's say, into sort of more constrained forms that the agent can interpret, right? So in this case, we basically convert these textual constraints into cost-specific variables. So in this case, it's like ETSI, MB, and MC are 3 different variables that are used by a state-of-the-art safe reinforcement learning algorithm, which is called the PCPO, Projection-Based Constraint Policy Optimization. And this is basically an algorithm that uses these variables to make sure that the learning happens without violating the constraints too many times. So We learn a constraint interpreter to perform that mapping, and then we also learn a policy network that learns a policy over the observations. These are the observations that are fed in. These are the constraints that are fed in, as well as the predicted constraints from these two models. Okay, so basically, this is one big giant neural network that takes, the observation that the agent has, any constraints that's given, and then it outputs an action, which is how it explores the environment, and it learns from a reward that it gets in the environment itself. Okay, so in terms of experiments, right? So we actually created a completely new environment because there actually doesn't exist an environment for learning with natural language constraints in the literature. So we created a new environment and collected some data from Mechanical Turk. So we explored three types of constraints. So one was the budgetary one that I talked about earlier. Basically you have a budget. You can't step on a particular tile more than X times, right? So you can imagine many different areas where this might be helpful, right? The other type of constraint is relational, where we want to say that you want to stay away from a particular location or for a particular type of entity with a particular radius, right? So for instance, you want to stay at least 3 feet away from the grass. That could be one type of relational constraint. And then we also have sequential constraints that tell the agent what not to do in a temporal fashion. So make sure you don't walk on water after walking on grass. It's one such example. Okay, so yeah, so we have a bunch of baseline models. So just to show you that this is not plain instruction following, we have a baseline model that is basically an instruction following kind of model that simply concatenates the text and observations as input. So it just treats these as instructions and not as constraints. And then the other algorithm is an algorithm called TRPO. So this is basically a baseline that doesn't care about the constraints at all, right? So this is just included as a baseline because I want to show you how, if you don't learn based on the constraints, you could easily violate them. And obviously, the cost violation is going to be very, very high. So the two metrics that we care about are maximize the reward and minimize the number of cost violations, right? So cost violation is something like you break your arm, right? You don't want to break your arm many times. So, right, so here's one slice of the results, right? These are just on the budgetary constraints. I put them up just for illustration, and additional results are in the paper. It's on arXiv, so you can go look at it. And you can see the two different graphs here, right? So on the left, there's reward. And these are the two baselines that I mentioned. One is our policy network, but with just a TRPO algorithm. And one is the CF model, the instruction following model with our, safe RL algorithm. And you can see, obviously it looks like, the TRPO algorithm does the best, mainly because it doesn't care about the constraints. It just wants to explore the environment completely. And you see our algorithm, which is POCO, is not far behind, right? It's able to almost get the same kind of reward. But the more interesting part is here, where you can see the number of constraint violations of all of these different algorithms, right? So basically, both CF and TRPO have a huge number of violations on average. So basically, in one episode, PN with TRPO is breaking its arm 8 times, right? So which is really something that's not really tractable if you're doing reinforcement learning in the real world on a robot, right? Whereas our algorithm, it's not perfect, but it has much less number of violations of the constraints that you add in that sense. So basically, we are able to learn a good policy while minimizing the number of times you violate the constraints. And all of this just by, when the constraints are specified in natural language, right? So in the future, the idea is, if you can scale these up to, other domains, maybe more real world robotics and so on, we can sort of allow humans to specify these constraints in real time through just language, right? You don't have to go program these constraints, and every time you want to change it. Whereas, you can just talk to the robot and say, hey, like today, don't go over the carpet, or tomorrow, don't go over the hardwood floor or something like that. So hopefully that gave you a sense. So yeah, I mean, I basically talked about 3 different pieces of work, but they all revolve around, how we can use language to specify something about the dynamics, right? Like either by restricting, in this case with constraints, or by giving more information about the dynamics itself, and so on. So any burning questions at this point, or I'll move on to the third part.
Yes, sir. I have a question.
Yep. Go ahead.
So I want to know about logical functions, because you say the transition functions and the reward function is the working together. So I guess there is some stages that you have to pass through in the logical functions part. So is there the many differences or the big differences compared to the transition functions or reward functions with the logical part?
Oh, that's a good question. Yeah, so this one, yes. So these usually, these logical constraints are usually in terms of the states, at least in these works. So basically what they try to do is like, so in this example, right? So there are boundaries in this case. So this is a Mujoko environment. So there's a humanoid over here, right? And the humanoid is learning to walk or run around in circles. And the boundaries here are the constraints. So in logical forms, how you express this is like, if the agent is beyond a certain X coordinate or below a certain X coordinate in this way. So it's based on states in these cases. In terms of dynamics also, you can specify. So for instance, where is this? Yeah, like the fan example is like sort of some dynamics where you can specify. So you can say like, don't fly into windy spaces. So by windy spaces, it's basically cases where, your prediction of where you are may sort of move around, right? Because of the wind, you can't really anticipate that. So that is sort of related to dynamics.
Thank you.
Sure.
I have a question. I think the constraint is very important part of the robotics.
Right.
But I think some constraints only for the training period. So yeah, do you have any idea, or is there any systematic way to get rid of the constraint along with some performance? I don't think.
With what? Sorry, the last. What did you say?
So along with the training performance, there was some index.
Okay. Yeah, that's great. Yeah, exactly. So our idea here is to, you're absolutely right in the sense that, usually these constraints are only during the training, right? And that's what we want to sort of change in some sense. Like, I mean, we want to make it such that, you can change the constraints on the fly if you can specify in language, right? So if the agent can understand all sorts of constraints, then maybe even during testing or even during execution, you can suddenly say, okay, I add one more constraint, and the agent must be able to just treat that as a hard constraint. But you're right in the sense like it does have an effect on performance, because if you impose more constraints, that means the agent cannot explore as much. And maybe it takes more time to learn, but that's a trade-off we have to make, right? So if you want to teach a robot, a trade-off in the sense like, I mean, if the robot breaks its arm, it's going to take maybe like a few weeks to repair it. So, but then it's okay maybe if it learns slower by a few days. That's a trade-off that we have to make.
Okay.
That's a good point.
Thank you.
Any other questions?
Okay. I really want to know why the action and dynamics is distinguished in the reinforcement learning, because when we in our intuition we cannot distinguish the action and dynamics perfectly, but when I learn about the reinforcement learning, it seems very difficult. It seems very important in to distinguish the action and dynamics in reinforced learning. And can you explain about that?
Yeah. Okay. Yeah, I think you're right in the sense like obviously, you know, the world is just a collection of actions, right? Like different things are changing the world state in different ways. You can think of even, you know, like I mean, the Earth rotating, you can think of it as an action, maybe if you think of the Earth as an entity. So you're right. So from the reinforcement learning standpoint, we always have this view of the agent and everything else. So the agent is what that particular, so the actions are basically what that particular agent can control in terms of exerting some influence, and everything else in the world is treated as the environment, right? So when we talk about dynamics, usually we are talking about the dynamics of the environment, right? So everything that is happening around the agent is related to the dynamics, and the action itself is basically whatever atomic effect or atomic change that the agent can perform that can result in some change in the environment, may or may not, right? So basically the idea is like you take an action and then the environment's dynamics basically computes the next state and then you're in the next state. That's the usual difference.
Thank you very much.
Sure.
Uh,
okay, sorry.
I also have a question. The example what you have like a spider or a chaser and like can explode, it is kind of state that the very restricted state that just go up and down or going right and left. But in the real state, it is very complicated to express the state and the action. How do you just use it in the real state?
Like real estate, you mean like the robot 3D space and so on?
Yeah, by restricting the robot, you have to describe the state at the robot and what action they can do. But it is very hard to express by robot, not by simulation or games. It's totally different. Yeah.
Yeah, that's a great point. So I think, have you seen this work on sim to real transfer? So there's some, I guess like OpenAI is one trying to do this. Like they have a Rubik's Cube demonstration with the robot arm. So the idea is like you can train a policy in simulation and then use that, you transfer it to the real robot. So you train it completely, the actions and everything, you learn it in simulation and then you transfer it. So I guess like if you have access to a simulator like that, you can build in rewards in this case and then transfer it to the real robot. That's one particular use case. You could also just have it directly on the real robot, but I guess then, you know, the descriptions will probably have to be more specific to that particular scenario, right? So maybe you can't say left, right, but maybe you can say something like, you know, the ball is unstable, it can roll off the table. Whereas you can say something like a square block is stable and it will stand, right? So maybe the robot then can figure out, okay, if it drops the ball is going to fall off. Whereas if it drops a block, it'll just drop on the table. So things like that may be useful. It doesn't have to be always about moving left, right, or things like that. It could be any sort of information that, you know, basically helps the agent figure out what is going to be the next state. Like if I take this action, what's going to be the next state? Like that kind of future prediction model would be helpful for planning, basically.
Then even the next state is not descriptive by yours, can it expect what's gonna be a next state, even if it is not descriptive?
Okay. Yeah, so that it can learn simply by watching what happens multiple times. So if I say you drop the ball and it'll roll off, I don't know what it means to roll off. Let's say the agent doesn't know what it means to roll off, but then it tries dropping the ball a few times, right? And now it's seen that it rolls off the table. And now if I say something like you drop something else, like you drop an apple or you drop an orange and it'll roll off, right? So now you already know the meaning of roll off. So even though it's a new entity like orange or apple, the agent can expect the same thing will happen with that because you said roll off before and it just went off the table. So it can learn this association. This is exactly the problem that we were trying to solve. So it has to learn this association of what it knows about the future and how we describe it in language. And if it learns this association, then in the future in the sense like if you train the robot to do something new task, then you just need to say the same, you just need to use the same language to describe things that you expect to happen.
Okay, thank you.
Sure. Okay, so maybe let me show you the last part, and then we can go on to any final questions, I guess. So, so the last part. So I talked about basically actions dynamics, right? So the last part is just about rewards, right? So how can we use language to understand rewards, right? So here's probably the most intuitive way I can think of to explain this, right? So the idea is like, we want to be able to teach agents just like how humans teach each other, okay? And here's an example. So I showed you these text-based games, right? So imagine this is a particular text-based game, right? You're here, blah, blah, blah. You take an action N. So these are short forms. So N basically means go north, okay? And then the game tells you can't go that way, okay? So the game is actually telling you something. It's giving you feedback. It's not a reward, right? It's just telling you, hey, you can't go that way, right? So this is basically some type of feedback that you're getting, and you probably learned now that, okay, how many ever times I try to go north, I can't go, right? So you've already learned that in one shot, right? So basically, the way that teaching happens between humans is often through language, whereas in reinforcement learning, one has to go and engineer these scalar reward functions, or or in the case of robotics, you have to engineer these cost functions and so on, right? But if we could just get agents to understand language and just use that as feedback, then we can observe them doing something, and then you can just tell the agent, hey, don't do it that way, right? Or that's not the right way to do it, right? Or you can say something like, yeah, you probably didn't want to drop the ball on the table, right? So this part is basically about learning rewards from linguistic feedback, okay? So this is some work that's led by Ted Summers, who's a student at Princeton, and also in collaboration with Mark Ho, Robert Harkins, and Tom Griffiths, who's also at Princeton. So the idea here is that, imagine that there is a learner, right? This is the robot, and it's trying to, let's say, play a particular game, right? So this is a game. It has to collect these different objects, and it doesn't know which objects give it positive reward, which objects give it negative reward. Okay, so it's just trying to learn. Oops. And the other agent that we assume is that there's a teacher, right? So the teacher, what's the teacher going to say? It's going to look at what the agent is doing, right? So the agent will move around a little bit, and the teacher will observe it and say, okay, pink is good, but go for the squares next time, right? So it's giving, the teacher is a human, let's say, giving feedback to the agent, right? So if you are the learner, this is obviously easy for you to understand, right? So if you are the learner and someone told you pink is good, but we'll go for the squares next time, then you will understand, okay, the squares are very important. Maybe I should go here, right? But obviously agents being able to do this is much, much harder, right? So here's an example to sort of put it into more context. So in 2017, Christiana et al., again from OpenAI, had this work on humans teaching robots. So the idea was like, there's a bunch of humans, and there are some RL agents. So the RL agents take some actions, and the humans look at those actions, right? So they look at the trajectories that these RL agents perform. Let's say the agents are some robots picking and placing a ball. They look at these actions, and then they give some preferences. So basically, let's say I give the humans 2 different videos of picking and placing. The humans will say which one looked better, right? And so just from the simple scalar preference of which one looks better, they were able to train these agents to do much better. Okay, so where do these humans come from? In this work, they used some, Amazon workers, right? So some crowdsourced workers that they used to help train their RL agents. So the interesting part here is, behind the scenes, what actually happened was the OpenAI researchers actually provided instructions to these human contractors. Okay, so in a game like an Atari game, this is the sort of instructions that they provided, right? So they told them shooting enemy ships is good, don't get shot for the game of Beam Rider. For Breakout, they gave some other instruction and so on. So in effect, what's really happening is in this scenario, humans are teaching humans to play, to be able to teach robots, okay? So what they're doing is providing some language sort of feedback to the humans, and these crowdsourced workers are then providing feedback to the agent based on preferences, okay? So if you keep this picture in mind, what we want to do instead is just provide some preferences to the humans and then use humans to teach agents through language, right? So we don't want them to sort of provide just preferences. We want them to directly tell the agent, hey, that is good, you did a great job, or you should have done that instead, right? So imagine just, again, this is like, if you imagine your robot can just understand what you're saying and just learn from that feedback instead of someone having to engineer a reward function. So here's an example of the setup itself. So this is from the view of the teacher. So what happens is, this is how we collected some data. So what happens is the screen on the right is actually what the learner only sees. So imagine the learner doesn't know anything about the environment, and it's just like moves around, tries to collect some objects, gets to see some score at the end of the game, but it doesn't know what's really the underlying reward function, okay? So this is what the teacher can see. The teacher observes what the learner is doing, and then the teacher can message the learner. So in this case, the teacher messages, nice job, you collected 1, 2, and 2, but the teacher can see that the pink squares are worth 8 points each, right? So the teacher says pink squares are worth more though, right? So the idea is like, this is then sent to the learner, and the learner understands, okay, next time I should go for the pink squares. So that's how this sort of works. So learner plays a level, teacher gives them feedback, learner plays the next level. Hopefully, learner gets better over time and time. There are 10 different rounds, and there's sort of like a randomized preference that we sort of instantiate every different game. So this is not, this sort of preferences are not shown to the teacher. The teacher just gets those 2 screens. But what we do is like, we just randomly, provide some rewards to each of these different object types and start a new round, and then, pair 2 people up, ask them to play with each other and so on. So to give you a sense of what the types of feedback are, right? So here are 3 different types of feedback, right? So like one is, you can say something like, keep it up, excellent, right? Or you can say, that's not a good move, right? So these are sort of looking at your trajectory, what the learner did, and sort of evaluating them. You could also be more direct. You can just say like, top left would have been better, right? So these are imperative type of feedback, which tells you exactly what to do. And then we also notice that, humans also provide descriptive feedback, which is directly saying, I think yellow is bad, right? So it's just describing the environment itself, right? Yellow squares are bad, light blue squares are high valued, and things like that. So note that these are all very different types of feedback, right? So to understand the first 2, you need to see what the learner has done, right? You need to see what they exactly did to understand the first 2, whereas these 2, you don't need to see what the learner did, right? You just, this is more descriptive. As long as you know yellow is bad, you can use that. So here's an example of how humans did with each other, right? So this is a precursor to what I'm going to talk about. But this is how, when 2 humans played with each other, you can see how over time, what happens is, first of all, the score increases, right? So that's good, right? So they learn, the teacher is able to teach the learner human effectively, right? So from the first level up to the 10th round, there's sort of a nice increase. Interestingly, the number of descriptive utterances decreases over time. So in the beginning, you talk more explicitly about like, these squares are good, these squares are bad, but then that decreases over time, whereas the evaluative feedback increases over time. So as the humans get better and better, right, the teacher is more focused on high level feedback, like keep it up, excellent, this is great, you're doing the right job, things like that. So it's very similar to, like, interesting, is very similar to how, teachers actually teach kids in school, right? So in the beginning, you provide very explicit information, But as the student learns more and more nuanced things, you're just providing feedback in terms of like, you did these things right, maybe this thing was wrong, and sort of like there's more fine-grained feedback that you provide. So yeah, so basically these were sort of things that we observed in the human-human study. And so now our machine learning challenge is to develop agents that can be very good learners, right? So we looked at 3 different models. There's a literal model that's basically performing some form of Bayesian linear regression. We use sentiment analysis plus a linear regression model to be able to do this. I'll show you in a bit. There's a pragmatic model, which is basically an improved version of the literal model. It uses the maxims of relation and quantity, which are basically some sort of theory of mind, which say that I sort of understand what the teacher is trying to tell. So the agent has an understanding of like how the teacher is thinking and uses that to understand things better. And then third one is basically a deep neural network that predicts everything directly. It's just as a comparison model. So here's a very good, probably like a sort of like an animated illustration of how this works, right? So in Bayesian linear regression, our job is to get a set of weights, okay? And we basically have a set of features, which are basically all of these entities, right? Think of every possible shape, 3 different shapes and whatever, 3 different colors, for instance. And this on the right-hand side, we basically have rewards, okay? So what we are trying to do is, suppose the agent is the learner, right? The agent has taken this particular trajectory, right? So now the teacher, who is the human, provides this feedback. That was terrible, okay? So now our job is like, this is a natural language. We want to convert it into something more manageable such that we can learn weights for the policy of the agent. So that was terrible basically means that you're talking about things that were seen in this trajectory, right? So these three sort of shapes here. So the features would basically be 1/3 for all of these. We predict from here, we have a model to predict this features. And then we have a model to predict what the associated reward is, right? So again, this is not provided to the agent at all. The agent just sees the word terrible and uses sentiment analysis to come up with a score of -8, right? Terrible is a bad word, right? Like, I mean, like it's saying that it's not a great thing you did. So it predicts that, okay, my reward should be around -8. Let's say the human teacher said bottom right was better, right? So now you're focusing on the bottom right, right? Again, the model understands all of this on its own. So using some NLP. So it understands all of this and then says, okay, these are the relevant entities. And then, it also predicts a reward, again, using NLP, right? So better means probably a good thing in terms of sentiment, so +8. And then similarly, we can do things for pink triangles are the best, right? So pink triangles, that's the only one activated. And you say, okay, +10, right? So now it's basically like a linear regression problem, right? So we have a bunch of features, bunch of rewards, and we can predict the weights here by performing regression. And we basically learn a set of weights to do this. So then, anytime you sort of provide any feedback, right? So you can use that to learn these weights, and these weights basically provide you an understanding of the world in the sense of like the reward function. You can use that to, again, train the agent to sort of get better over time. So basically, every round the agent plays, it gets some feedback, and then it gets better just by incorporating that feedback. So here's a quick demonstration of that, right? So we had 2 different settings. There was an offline setting where I said, we collected some data offline. And, these are the results for those 3 models for that. We trained the Bayesian regression model, we had a train set, test set. But you can see that, the mean normalized scores are around like 35 to 40 for the best model, which is pragmatic model, which is not bad. But then what was interesting was we then took that model and actually performed a live test. So basically what we did was like we took this train model, put it on Turk, and asked it to play with humans real time, right? So basically it's provided a random game, only the human knows what the underlying reward structure is. It starts exploring, the human provides feedback, it learns on the fly, like completely online active learning kind of setup where it starts learning live completely. So interestingly, on the live scenario, right, we're almost, the pragmatic model is almost getting the same score as a human, which is basically telling you that it's able to actually effectively understand what the teacher is saying just in pure language, right? No reward functions, nothing, right? The teacher is just providing feedback through language, and it's able to do almost as well as human. So basically, you know, the sort of pragmatic model is pretty good. It's able to understand just feedback completely in text. So again, this would be something that, again, like this, I know that the setting that I described is a very simple game, but you know, if this technique was to be scaled up, right, it could allow you to basically reprogram your robot to do several different things, right? Like, and provided feedback in some sense. So let's say it's performing a particular task and you don't want it to do a certain thing, like maybe knocking over the glass or something, then you can provide feedback saying that's not the right thing you did, and hopefully that helps the agent, you know, adjust his policy and learn to not do that the next time, for instance, right? Okay, so I think that's basically all I had. You know, the sort of idea that I wanted to convey was basically, you know, reinforcement learning is great, but if you want to scale it up to more and more environments, you know, and be able to allow us to train RL agents in a more free-form manner, right? Like through just instead of going back and reprogramming the code and things like that, natural language is very, very essential. And in this sort of talk, you know, I showed you several pieces of work that we have that hopefully give you a sense of like how we can incorporate language into several parts of a Markov decision process, right? So, or just generally control, right? Things like actions, dynamics, rewards, and so on. And basically representing these different aspects of the RL framework with some more semantic structure can help speed up the learning, as well as help generalize to new scenarios, right? And hopefully in the future, you know, we can also look at, you know, identifying the type of information conveyed. So in all the cases that I mentioned, the agent already has an idea of what the text is trying to say, right? Like, so all the models were kind of specialized because, you know, in the last one, I showed you that we are already expecting the text to talk about rewards, right? In the first one or the second one, I showed you how we're already expecting the text to talk about the dynamics. So that's sort of like a prior built-in, but maybe in the future, you know, we can just develop systems that identify that on the fly, right? So I say something to you, and then I say something to the agent, and the agent figures out what type of information it was. Is it talking about a reward? Is it talking about the dynamics? Is it talking about some instruction? So all of those things could be done in the future. And of course, you know, all of the most of the stuff that I talked about, they don't really have a tight integration of like more perceptual signals, like for instance, like, you know, visual signals like pixels and so on from cameras and so on. So future work, you know, can work on, you know, integration of more of these, and probably also like more contextual understanding, right? Like, and by context, I just basically mean the world around us, right? So more of the context that's built, better these systems can sort of become. And the final thing is basically, you know, like much of RL is focused on the single task, single environment benchmarks. Like, you know, you try to train an agent for a particular task and it only does that. So we need more work on focused on multiple tasks, multi-environment kind of benchmarks. And I think that would really help, you know, make these things more generalize better, and not just focus on one task. So yeah, I'll leave you with that. You know, if you want to take a look at any of the papers that I mentioned, or, you know, other materials like code and data, you can go to our lab website. And other than that, I'm happy to take any more questions right now. Thanks.